Okay, everyone, let's talk a little bit about our worksheet 2, diode approximations. We'll dig into a little bit more of the real world of how diodes work rather than the ideal. Remember that the ideal, we said, a diode is either open, like an open switch, or it's conducting and it's a piece of wire. So it's a perfect conductor or it's a perfect insulator. It's not in the middle. But in the real world, we know that when the diode opens up, once it's a go, we do drop some voltage. It has some resistance, some voltage that it's taking. So we see that our diodes in our circuits become 0.3 for silicone diodes, or 0.3 for germanium diodes, or 0.7 for silicone diodes. There are other types of diodes we'll learn about later, light emitting diodes. We're going to learn about Zeners here very shortly and how they act differently, but they're all part of the same family and they all have similar characteristics: forward and reverse biases, voltage drops once they're conducting an amount of resistance and current, just like a resistor, and we can figure that out. So how do we go about our page here? Let's just go ahead. On our worksheet, we have a couple parts to the worksheet. The first 2 pages are where we're going to record our values. Page 1 is our silicone values. We're going to assume that our diodes, when they're a go, they're 0.7 for our second approximation. Our page 2 is going to be for our germanium diodes. So page 1 silicon, page 2 germanium. When our germanium diodes are a go, they're 0.3 volts, not 0.7. Second part of this is page 3, which is the instructions. The instructions tell us how to find the logarithmic approximation. So that's the third entry in each one of your series of 3 measurements that you take for each diode. So what you want to do there is you want to follow the instructions. We'll get into a little bit more how to do that. And then the last 4 pages, 5 pages, 1, 2, 3, the last 5 pages are graphs. Okay, these are similar to what you would see in a data sheet that you would find on Mauser or DigiKey or really anywhere over the internet. The first 2 pages are for silicone diodes. And we can see on the left-hand side, the voltages stay pretty much the same on the bottom. But on the left-hand side, we'll see that our range of current is different. On page 4, it's 0 through 12 milliamps. On page 5, it's 0 through 120. Pick the right sheet. You want to pick, if you're under 12, pick the 12 scale. If you're over 12, you're going to have to pick the 120 scale. For our germanium on page 6, our scale is 0 to 1.2. Page 7, it's 0 to 12. Page 8, it's 0 to 120. So again, choose the right pages for those sheets. All right, let's take a look at the first page. We have recorded values. I'm doing a gimme here so that you can see the values for the first problem on the worksheet. All right, and so what are we doing here with this? How do we figure it out? Well, we'll look at the same here. We've got our germanium gimme as well, so that you've got something to at least compare it to. We want to make sure again that our silicone diodes, if they're conducting, they're assumed to be at 0.7 volts. Our germanium diodes, if conducting, are assumed to be 0.3 volts. This doesn't mean all or nothing, however. When we look at our curves, they tell us that as the voltage increases, current begins to grow very quickly after something like 0.6 volts. There's a knee, they call it a knee current. It's right where it goes from hardly conducting at all to quickly coming around the corner and shooting up in value. That knee is where the diode starts to turn on. All right, so let's take a look at that curve here. You can see the knee right at about 0.65 volts through to 0.7. And on our instructions page, it tells us find the current with the diode shorted. Okay, and then it tells us find the voltage across the diode with the diode open, and use this to come up with your currents per volts. Okay, so if we have IT divided by EA, let's look at, we have 100 milliamps divided by 5 volts, that gives us 20 milliamps per volt. Okay, so in this example, 1 volt, our current is at 100 milliamps on the left with the leftmost pink dot. And if we take off 20 milliamps by going over 1 volt, and we graph a line, okay, this is what's called our load line. And this is another way for us to figure out what's happening with our diode. Okay, so again, we just kind of take a look at the 3 steps. Find the current with the diode shorted. If we shorted that diode out and just turned it into a piece of wire, what would the current be? It would be 5 volts divided by 50 ohms to give us 100 milliamps in the series circuit. Then we would look at the diode as though it was open, treat it like a switch. What would our voltage potential be across that diode? It would be 5 volts. It's an open switch, so all of our voltage is across that infinite resistance. And then find the current per volts. So we'll take our 100 milliamps, we'll divide that by our 5 volts, and that gives us 20 milliamps per volt. And that's how we graph that line that we talked about. All right, so again, diode curves, you'll find them in a data sheet. And again, 5 are included in your lab, 2 for silicon, 3 for germanium. Make sure that you choose the right one for each problem. Here is the curve that goes with that 5 volt 50 ohm circuit, and you can see that the diode crosses that load line right at about 0.78 volts. Okay, so let's just take a look at the example. Here we are shorting out our diode, and we see that we have 1 volt across the resistor. And in this example, our resistor is 1 kilo ohm. So for our first line, the E of R1 is 1 volt. The E of diode 1, energy of diode 1, is 0 volts. And our current for our total is 1 milliamp. Okay, our second approximation. Let's take a look here. For our second approximation, we say that the diode is a go. Okay, and with that diode being a go, it's going to take its 0.7 volts. It's a silicone diode. So our silicone diode taking 0.7 volts, that leaves 0.3 volts left for R1. Our new, in the non-approximated, more accurate example, we have 0.3 volts divided by 1,000 ohms, 1 kilo ohm. That gives us 0.3 milliamps. And again, I could write 0.3 milliamps as 300 nanoamps, but I'm comparing things, so I want to keep everything in the volts in volts. I don't want to be switching to kilovolts or millivolts. I don't want to be switching. It looks like predominantly I'm going to get millivolts out of this, so I want to try to keep things, express them in milliamps for my current, so that it's easy for me to see what's happening. If I'm switching all over, it's harder for me. So in this case, the engineering notation doesn't help us if we follow it strictly. So we're going to stay with milliamps and we're going to stay with volts. Okay. Now, so that's our first two lines, pretty simple. The first one is I short the diode out. What do I get? I get 1 volt, 1 milliamp. The second one, my diode starts to conduct. I get 0.7 volts. It's a go. It takes its 0.7 first, and then the resistor takes the rest of the voltage. Once I know the voltage at the resistor, I can calculate the current. So then the diode says whether the circuit's going to turn on, but the resistor says how much current it's going to have based on how much volts it's given. All right. So then we look at how to make the load line. The rules for the approximation say short the diode, find the current when shorted. So the example 1 is 1 volt. Rule 2 says find the voltage of the diode when it's open. Now this is for the load line. I know I just told you, you know, for the approximations, the first one is, the diode is an ideal diode. Second one, we say that it's not ideal, it's going to do 0.7, but now we're finding the load line, just how we graph this load line. So what's the diode voltage when it's open? What's the diode when it's shorted? What's the diode when it's open? And then rule 3 says find the current per volts. So I'm going to find a sheet that has, for my silicone diode, that has my best range, and I know that I'm in the 1 milliamp range, so I'm going to pick the closest one that's going to give me the most resolution. If I picked the 120, it would be so small I could hardly tell what was going on there. So I want to graph it for this. So I go on the left-hand side, I find my 1 milliamp. My divisions going up are 0.4, so I have 0.4, 0.8, 1.2, 1.6, and then 2. So my 1 milliamp is directly between the second and the third tick up on my vertical axis. And then when I go all the way over to 1 volt, I put that down at 0 because I have 1 volt in this problem, and my current reduction is 1 milliamp per volt. Okay, so then I'm dropping that down all the way to 0 there. All right, and if we then go back to our sheet and we take a look at what happens there, I can see that my arrow is intersecting right here at about 55-ish, 56-ish, 0.55, 0.56 volts right there. And if I bring that back, I said this was 0.4, this is 0.8, this is 1. So I kind of have about, if this is 55, maybe I'm up to about 45. Probably would have said not quite 45 on the milliamps, but at any rate, if I follow my graph, my diode is 0.55 volts. That leaves the rest of the 1 volt for my resistor, and then my milliamps accordingly. Okay, and this last piece of instruction, it just basically gets into an issue where we're trying to say, if you're given 1 volt on your voltage source, we already know that whatever current that you calculate is going to be it's going to be X current per volt, and that's what we're looking for. So 20 milliamps, 30 milliamps per volt. If you have more voltage than that, it just wants you to divide your total current by your total voltage to get to current per 1 volt, and then that is what you would graph. At 0, you would graph up your total current per volts. and then at 1 volt you would graph down a loss of whatever currents per volt